evening, all of you, and good morning to Dr. Krishna. So it's a pleasure to have this talk on differentiable world models for physical AI. A short introduction to Professor Krishna. So Dr. Krishna Kumar is a J. Neil Thompson Sentinel Teaching Fellow and Associate Professor at the University of Texas at Austin, and a core faculty at the Oden Institute of Computational Sciences. His research is at the intersection of AI/ML, numerical simulations, and robotics. He directs a $7 million NSF-funded national ecosystems for AI integration in engineering, and he received an NSF Career Award in 2024. His research involves developing physical AI and control methods for autonomous manipulation of deformable materials and navigation in extreme environments. As an educator, he received the Dean's Outstanding Teaching Award and runs coding clubs for kids at Austin Public Libraries. It's a pleasure to have you here. So the floor is open to you, Professor Krishna.
Thank you, Professor Sinha, and thank you so much for having me, and really great to present my work. Okay, we'll start with what I want to do with AI. It's been transforming a lot in large language models, generating videos, but bringing AI applications into physical worlds has been a big challenge. And most of it could be robotics, but it could be other control aspects. So when AI comes into the physical world, they must be able to transfer across domains. So most of my work is around rovers or in deformable parafoil type systems, and also like structural monitoring work. So for example, when we say like it needs to be transferring across domains, we are talking about we build rovers on Earth and then deployed on Moon and Mars, where we've never collected enough data to train robots. So be able to go across domains. Be able to go across tasks like manipulating soft deformable objects like sponge to caring for patients with different, or even doing a surgical robotics type applications where you're manipulating soft tissues. And finally, across different platforms, because we not only want like very fast simulations in certain cases, to be able to do simulations at different levels of fidelity and controls at different levels of fidelity. So we go into this world models. World models basically mean that's our understanding or representation of what the world looks like. And this have different fidelities, and people have used like Mujoku type RL simulators, which have efficient physics, but they don't really model the contact rich nature or the deformable material. It mostly is limited to rigid bodies. It has very simple visuals, so there's always a sim to real transfer issues that happen. So people have started moving more into physics engines. So these are your game engines where the physics is slightly better. Visual fidelity is what people prefer here, but it's often unrealistic. So like BeamNG can model like driving on asphalt, but if you try to drive the same car on sand or in grass, then they either assume it's a rigid body or you can't move, or it doesn't get stuck as usual. And then you often have these high fidelity simulators, which is what my PhD was on. So I come from a numerical methods background and see all these high fidelity simulators, which take months to run. So you can't do millions or billions of particle simulations interacting with the rover to be able to train a RL algorithm on it, because even if it takes like one simulation takes a week or a month to run, you're never going to hit like a million simulations needed for RL. But on the other hand, I don't know if you hear the sound, but here is a text prompt which gave to Google's Gemini, which is like, create me a lunar rover world, and it is interacting with the soil. And if you play again, you can see the video is very realistic, but I want to observe one aspect where it is going to try to scoop the soil, but it is scooping the soil the exact opposite of how we would do. It's just push the scoop forward, it tries to scoop backwards, and the soil jumps onto the scoop, which is like everything non-physical about it. And if you heard a sound, it's also like scratching the surface in a vacuum where there's no environment for the sound to travel. So visually it looks stunning, but physically it's unrealistic, although it only took like 3 minutes to generate it. The goal is, can we do this creating these world models which are interactive, but make it physically right, and maybe add one more step, make it fully differentiable so we can go do controls. So that's what this talk is about, is how do I create these fully differentiable world models which we can then use to learn or to do robotic applications. So would say my area of research in the differentiable world model for physical AI focuses on these 4 aspects. The 4th aspect of guarantee is still in progress, but we started out with see or sense, where we're going to capture the world that we live in and then represent it into a 3D model. Then we're going to talk about predictions, how we manipulate these 3D models or systems. And then once we are able to do this in a really fast way, we're going to do action or controls. We're talking about transferable controls, zero-shot approach, where we can take the models which are trained in offline and then zero-shot put it in a completely new environment and see how they behave. Ideally, we want all of this to be safe. That is, my control actions are guaranteed to not crash my rover. We're going to also look at some examples where we're trying to drive a car at 50 miles an hour. So we want it not crash and then follow a path, and then you can have different levels of controls there. That work is just started, so we have some preliminary results, but we'll present to you this whole framework of where we are going with this. Okay, so let's look at seeing or sensing. We're going to start off by capturing the real world, and one of the nice ways to do it is called Gaussian Splats, which came out in 2023. Our group was doing differentiable rendering to go from images to 3D models, and it became NERF, and now we primarily use splats. Splats is basically take multi-view camera images, and you're going to represent those camera images with millions, if not hundreds of thousands of blobs of Gaussians, each with color and representation. So what it would actually look like is what you see on the left, but I'm showing you the centroids of these Gaussian blobs so you can really see is like how it is represented. So what is a splat? A splat is basically a 3D Gaussian ellipsoid. So if you think of a Gaussian distribution, just make it into a 3D, and you can define a position. You can have a shape which is defined by the covariance, which describes your ellipsoid's shape. You can add color and spherical harmonics. This is like your view-dependent lighting conditions. So if I have the same object, look at it from different views or different lighting conditions, we can manipulate the splats to have different colors based on your views. And then finally, we add some sort of transparency. From a rendering world, this is basically saying how many splats do I have to render behind, so I don't have to do a full render of the entire scene. So what this does is we can take pictures of your objects in 3D, or you can take a video, and we're going to try and represent this as splats. The first step we do is structure from motion. This is not necessary, but this is the most common way to do it, is to initialize all those 200,000 Gaussian blobs at a reasonable location. So we start with a sparse splats of these blobs and locate them. Then we do a render, so we can compare what we see and what we think it looks like, and create a loss function. So you do it multiple times, compute your loss based on different views, iterate until your loss is optimized, and you get like a really good 3D representation. So start with a initial position of Gaussian blobs, splat it to render, compare your image loss against the pictures you had, differentiate through the whole pipeline, and then you optimize it until you have this nice 3D model. Now that we have this 3D model, I want to not just say I have a world which I can simulate, but I want to add some physics to it. But the main complaint I had with the Gemini was it was doing something non-physical. So what if we add physics directly into these blobs? So one way to add physics is called material point method. It is, for those familiar with like finite element type simulations, it's just very close to it, except MPM allows you to do large deformation problems. So in finite elements, you discretize your domain into mesh and you solve your equations of motions at the mesh. Here, we discretize your domain into material points. So this is equivalent to doing Gauss points in FE, except the Gauss points can move through the mesh. So what we're going to do is now project that Gauss points into the background grid. That's where we are going to solve the equation of motion and then update the particles. If you look at these Gauss points and the Gaussian blobs we had, they kind of share a similar property. Both are discretization of our 3D representation, except in this discretization, I have material properties and constitutive laws, which I can model. So we go back to our Gaussian blobs and we add a little bit of physics. So each of the blobs is now going to take a particular type of physics. So what type of material it is, what is the deformation? If I want to add some forces to it, we add that and do a joint optimization loss so I can compute how the physics is going to evolve. So that means once I do it and I think, oh, this plant is going to behave like a viscoelastic material, pot is mostly elastic, I can do this. Where we have taken a 3D model and you apply the material properties, and you can see if I put an action like create gravity, and you can see how that material deforms very well. But you can have a lot more fun with it. It doesn't have to behave like this, which means you can assume the entire material is made out of sand, or even not. This is non-physical, but we're just showing like what you can potentially manipulate it. And you can see the center one is more physically realistic of what could likely happen, but we have this full capability of simulating different sections of your 3D model and make it look realistic. So that's the see and sense part. We are able to have the model. Now we've started to add some simulations to it, so add physics to it. Our next step is to do predictions. So we want to know, okay, if I deform this material, what is the material property, or what forces were acting on the system? And mostly this is basically like doing a system ID based on your videos or even sensors that you may have. So that's what we're going to focus is the prediction part of the cycle. So prediction part means so far we've been running simulations forward. So I assume certain material properties or state IDs, march forward in time, use any of your traditional simulators, get a result. But we often observe a result either using your physical sensors or through perception, and we want to go backwards to figure out what is the initial system ID, material properties, or control parameters that we need. And this is, you can call it optimization. Numerical methods will call it inverse problems or design. All of this is same. It's basically trying to calculate the gradient of your result with respect to your input parameters and update based on those gradient values. Typically, you could do a finite difference type simulation to calculate what is the gradient of your result with respect to input parameters. But that means you need to run at least two simulations. One with the current input parameters, change your input parameters slightly, that is your delta, and then see what is the change in your result. Instead of that, we're going to use something called automatic differentiation. For those of you who've done machine learning, this is basically backpropagation, but we're going to leverage this backpropagation in lots of different ways. So just to give you a brief overview, how backpropagation works is, let's say I want to do a simple calculation, y equals x1 squared plus x2. I'm going to apply x1 is 2, x2 is 3. We lay it out as a directed acyclic graph. So each of the computation represents a node. So I'm squaring it, then adding it, and then get the results. To get the results, which is your forward pass, just put in your values and then follow the flowchart. You get your results. Nothing fancy here, just setting up the problem. But how backpropagation works is this nice thing where you can pre-compute your gradient of each node with respect to the other one. So in this case, I can calculate what is the gradient of y with respect to W4. Or more interestingly, when we did the multiplication, we can pre-compute the gradient, that is 2 times W1. And once you've pre-computed all of this, if you now want to calculate the gradient of y with respect to x1, all you need to do is to apply the chain rule. So take all your gradients before, multiply each of them through chain rule, and apply the value of x1 is 2. You will automatically get the gradient of y with respect to x1, which is 4. If you did find a difference, you will have a small error, but doing it in backpropagation means you have absolutely no error. It is very precise, and it is able to create a graph for any computation that you want and backpropagate through the whole simulation. So what we did is we take the traditional material point method that I showed before and make it fully differentiable. So we rewrite the code to be fully differentiable, like lay out a directed acyclic graph. And every time as you march forward in time, you're basically extending this graph in time. And finally, you have the result, and we are going to backpropagate through the entire simulation. You can define whatever loss function you want, whether it's the error and displacement or the control parameters that you want, but you can backpropagate to any input properties or state IDs that you want to estimate. Except it looks very scary. This is a single point of directed acyclic graph. So if you think of the mesh I drew, and I'm adding a single node in that mesh I had with the MPM point, that has so many connections. And each of those connections will have its own flowcharts of tags connecting to it. So it is quite big, and differentiating through this requires us to do some gradient checkpointing and other memory management issues. But it opens up a new way of looking at our traditional simulators. And so what we did was then let's do a state ID. In this case, I'm trying to go and estimate what is the material property if I observe a dynamics. So this is actually NASA's problem. They want to excavate and figure out what the material property is on the moon. Last time we tested the material property was in 1970. That was a single soil test that we did. So we don't really know how the soil would be as we land in different locations and try to manipulate it. And NASA also forgot to put sensors or other control systems. So they have 2 cameras, and they were like, let's figure out material properties with this. So what we decided to do was, can we plow through the soil, and looking at that dynamics from multiple angles, can we figure out what is the material property? In this case, friction angle. So very quickly, friction angle is basically if you pour sand and then it creates a heap, the angle of your heap is basically the material property that we are interested in. But unfortunately, because there is no very little gravity and no atmosphere, pouring sand is not as easy as you would think on the moon. So we need to recover this from the dynamics itself. So we take multiple views of the system we have, do a splat that allows us to get the 3D model, add material properties like we did. This time we are just going to guess what the material property is to start with. March it forward in time, so do a traditional forward simulator, compute the loss at each time step because we have a recording of the video. And once you have all the loss, aggregate all of those losses and backpropagate through the entire simulator. And we can now calculate what is your gradient of this loss with respect to our input parameters, which is the friction angle, and that allows us to see what is the friction angle. So we do know what this is because this is a simulated world that we created. And we can see what is our loss for different friction angles. And we did this in 3D, and that's our real experiment, but it is synthetically generated with MPM. And we get pretty close to the lunar's friction angle, which is about 45 degrees. In Earth, most sands have about 30-degree friction angle, and lunar gravity and lunar soil have like much higher friction properties. So this allows us to do state IDs on a single material property, but you can, of course, do this on multiple system parameters or to do control examples. So here we're using the gradients which we get from our simulation to basically control how much torque that we need to apply on the rover here. So this is the razor which NASA uses to do manipulation of our system. And we constantly keep moving the target, and you can see the environment is also continuously changing. And that's one of the difficulties, is you need to now not only control your system, but also control it in a state which is continuously evolving. We've used the same differential MPM to look at structural health monitoring, which is on old bridges in London. So this is a railway bridge. So we don't know what is the load on the bridge, because we know what is an empty train weighs like. We also know what a full train weighs, but we don't know what is the exact load that went on as we recorded some measurements here. But using differentiable MPM, we can find out if there are any cracks, what is the stiffness of our system, as we estimate on the unknown, which is both the force as well as the material property. And we were able to recover back the correct stiffness in different regions to see where that crack is located. So all of this is slow. I'm doing a gradient through an extremely slow simulator. This takes like few hours to do, but few hours is still a lot if I want to train autonomous systems. So I want something way faster. So let's say I'm looking at a flow of granular material, which takes about 3 hours to run using a traditional NPM type simulator. I want a system that is reasonably fast and be able to replicate most of the dynamics. I'm not trying to replicate the entire dynamics exactly, but majority, so 95% of the dynamics, but in a reasonable amount of time. This is where graph neural networks become useful. You can see here that the dynamics look pretty similar, but it runs in about 5 seconds rather than 3 hours. So that opens up what we were interested in, really fast targets, which are able to replicate the system, but does reasonably well. But if you want to look at errors, look at the front of the flow, there are separations, whereas if you look at the GNS, it only it gets it slightly wrong. But the overall run out and the dynamics looks reasonable there. But I did say it takes 5 seconds, and what we often don't hear is how long it takes to train them. And in this case, it takes about a week on a single A100 GPUs. But the good thing about GNS is in GNS, rather than trying to learn the entire system dynamics, you're actually learning the local interactions, which means we can do this training on small scale systems and scale it up or completely change the geometry. So the way it works is you take your system, represented as a graph. So each of your NPM points can be nodes in your graph now, or it can even do collection of NPM points as nodes in your graph, and represent the interaction between those nodes as the edge interaction. And this is encoding, so where we go from the physical state to a latent graph. And message passing happens fully on this latent graph where the graph structure doesn't change. And then finally, we're going to go back from this latent graph to a physical space to recover the next step. So we do it at each time step. Take the current system, push it to a graph, and then the dynamics evolve in the latent space inside the graph, and then we decode back to a physical space. If you want to try out, our code is public, and you can train our graph neural networks on any of your high-fidelity simulators, both particle-based systems and mesh-based systems. So the way it works is you take your physical state, like mass, position, whatever properties you want, push it through a neural network, and that gets a fixed size latent vector at the nodes. You also get a relative positions and everything in your edges. And the edge message is basically the edge feature, receive a node feature encoded to a finite dimensional latent space. Once you have the message, you basically look at the node and see what are the other nodes which are connecting to it, and do a superposition. So literally sum over all your messages, and then use the updated updated node feature to update your nodal information. So create a message on the edge, aggregate all the messages, which is aggregate all the information on the edge back to the node, and that basically updates your nodal state. And you can do it multiple steps, and then finally you decode it. So you take the updated nodal feature and decode it into a physical condition. In this case, we basically use the decoder to predict the acceleration and multiply by delta t. That gives us velocity at the next time step. And you use a semi-implicit Euler update to update the position of the particles. If you want to update stress states, you can also do it, but without having to do the time step, you will do it stress update on the current properties. The good thing about this is, like I said, because you learn local interactions rather than the global dynamics, you can train it on small scale system and scale it up. So this is 8 times bigger than what we've trained. But what I like more than just scaling up is changing the geometry completely. So we've only trained it on a single barrier system, and we are able to predict the dynamics in completely different configuration. This is what makes it nicer, where you can spend a lot of time training it and be able to deploy it under different dynamics or different boundary conditions. So going back to the differentiability aspect, I did say differentiable MPM was great, but it took us a significant amount of time. Graph neural networks is entirely based on backpropagation and MLP, which means I can differentiate through the entire GNS simulation. So each one takes about 5 seconds. So if I want to do a design optimization where I want to control how far a material runs out, I just need about 30 iterations, each taking 5 seconds. So in about 5 to 10 minutes, I will be able to optimize the entire design for this barriers. It does generalize pretty well. In this case, we trained it on an aspect ratio of 1. In this case, aspect ratio is the height to the length. So geometry, we trained it on a single geometry, and we are trying to predict on multiple shapes. So you can see here the dynamics actually changes. So as you go from short columns to tall columns, the purely frictional to more collisional regimes. And we trained it on 3 different friction angles, and it works reasonably well across geometries. But the issue in MLPs or machine learning is not interpolation. Whenever you're interpolating, you're pretty good. And in this case, we trained it on 3 friction angles and tried to interpolate in 25 and 35 degrees. Everything was great. Once you try to extrapolate, so go to very low friction angle or very large friction angle, things completely fail. So here we're showing you like this is the domain where the friction angle is pretty high, or we even added cohesion, which is kind of stickiness to the particle. So think of like clay material or dough, like either chapati dough. Now I want to take my sand model and model a dough, then it is not able to capture the dynamics because it has never seen a dynamics like this. So the normal solution is, okay, fine tune it. I have already a trained model. I have experiments where I'm simulating a dough, or even physical experiments of doing a dough compaction. You can fine tune it, and those are the entire model being fine tuned, which is the blue bars where we get pretty close to the actual behavior. But fine tuning still takes time. You only tune it for a single new condition. Now you want to be able to adapt to multiple conditions. So we thought, let's try a different approach. We know the most important part is the first couple of message passing layers. So rather than adapt or train the neural network to different materials, we are going to adapt the latent space directly itself. In this case, we are going to do an affine transformation. So we take whatever the new material property is, like cohesion, for example, which we didn't have, accept that as an input through a tiny MLP, but then project it to a latent space, which is affine transformed. And we are trying to say, how much do I need to transform this latent space so that it is able to capture the dynamics well? And we will do it across a range of new properties. So rather than having a single fine-tuning case, we are going to adapt it over multiple spaces. So that's our film-based adaptation, which allows us to say, give a new property like cohesion, and you can see this is our ground truth. The pre-trained model doesn't capture it well, so you can see it especially in cohesion of 1.25 kPa. And the fine-tuned model is only tuned for this particular cohesion that replicates it very well. You would expect it to do it because you're only training it on that material. And this is our adaptation where we are able to capture the dynamics without having ever trained on 1.25 kPa. And the good thing is it only takes about 15 minutes to adapt a 1 week long simulator to a completely new setting. And these are our results. So we can see our film and fine tuning both give like roughly the same results. One thing is fine tuning is being done for each of those cases, whereas film is done once and being applied both inside and outside our training regime. So what we do is we now have a very fast surrogate model, which can adapt to different scenarios. So we're going to capture a lot of videos of different complex sites. This could be like hostile territories or construction sites where it is really messy, and be able to convert it into a 3D Gaussian splat. So far, it's been exactly the same as you've seen before, except this particular scene is pretty large, and with 5 million Gaussian splats, it takes about 8 seconds to render on an A100 GPU, so it's pretty fast. Now we can identify what these materials are, so use a vision language model to identify it, apply a reasonable enough good initial guess, and now you can try what happens if the entire things get rained on. So imagine trying to drive on these slopes, but now imagine what will happen if it rains. The good thing is you don't have to worry about it. Now you can simulate it reasonably quickly with different wheel types, different configurations, rapidly adapt if you have new videos of what's happening. So we took a truck scene from a completely different environment and drove the truck straight into the sand to see how such a system would behave. And we can guess what the material property is for the truck from our VLM, assign those, apply GNS, and then simulate this behavior entirely. So this works well, which means you can have full-blown pipelines where you can literally type in text like simulate a 3D water interaction with pagoda. And an LLM agent will figure out simulation parameters, generate the 3D model, splat it, apply GNS or NPM, and simulate what will happen during a natural hazard scenario. This is a car of one of our undergrad students, record a video, and again, segmented, apply material properties, and simulate what will happen if you hit it with a tsunami. They like hit everything with a tsunami. And this is our text to simulation. The first part is not ours. The first part is DALL-E or any image generation system. But once you have it, we have a latent space diffusion model that will generate a 3D object. Splat, NPM, sim, same pipeline, but shows the versatility of the method. So each of them takes about 5 minutes. So going from videos to a full simulation in under 5 minutes. The simulation takes less time. It's just the call map and others take longer to generate the 3D model. So we're coming to the last section of act and control. So we are able to predict, we are able to do state IDs, and our next step is to be able to control these systems. So this is where we've seen some sort of adaptation to film, but now we're going to focus on either learning the dynamics of the system in a zero-shot manner and then being able to control that system in a zero-shot manner. So the adaptation is basically we've trained it on this system and we want to either deploy it to the moon or deploy it to the Mars. How can we do it by not getting a huge amount of new data, but also in a zero-shot manner? One traditional approach is transfer learning. It's been around widely, so do it on different tasks and be able to generalize across robot manipulations. But we wanted to leverage something more fundamental in a mathematical space. So we wanted to go to Hilbert space where linearity is preserved and see if we can leverage some of the Hilbert space properties in the zero-shot learning. So I'm going to talk about some of these, some of our approaches that we've been developing in this space. which is how can we represent our problem in Hilbert space. So we're talking about functions. So most of our control and results we get can be represented as functions. So let's say I want to approximate all quadratic functions. So you can represent this as a basis function where it's a constant, it's a linear, or it's quadratic. And once I have this basis function figured out, all I need to do is figure out what are the representation, which is what is the coefficients. I need to multiply this basis to represent any function I like. And this means I learn a basis function and I learn coefficients, I will be able to generalize to any function in that Hilbert space. That's essentially our function encoder approach, is use a neural network or use multiple neural network to learn the basis functions. And once we have these basis functions learned, we are going to use least squares to figure out what the coefficients are. And the neural network stays fixed once you've done the offline training part. And the online inference is a very simple least square solves to compute the coefficients, and you have your new function state. So essentially, start with multiple functions, and unlike most operator learning approach, we can sample at different rates. We are not limited to fixed sensor locations or fixed sampling rates. All we need is your function value and where it was evaluated as a pair, which you will generally have. And then you can even have sparse or dense representations or variable representation. Train it, so where our neural network is basically trying to spread out the basis function. So make sure you have enough data point so that this basis functions become orthonormal. You can do like Graham-Smith approaches to make this orthonormal, but we found that eventually, if you have large enough samples, even the least square solve gives you roughly orthonormal basis functions. We can add additional losses if you like to make sure that this loss function, this basis functions are orthonormal to each other. And then in the online inference phase, we get a new function values. So all you have to do is take a dot product between the function values and your basis function. You get your coefficients. And once you have your coefficients, this is where we are going to train our dynamics on or train our control parameters on. It's a low dimensional representation. You're not representing a high dimensional function space. You're representing the coefficient, which is your latent space. And you can either condition your control policy on this low dimensional space or condition your dynamics in the low dimensional space and be able to predict. So the first part is learn a space of input functions. And now we are going to, because I've shown you so far how to do it on one space, now we're going to do it both on the input space, which could be your forcing functions, and also your output space, which could be your displacements or velocities or stresses, whatever your output space is. And each cases, you're going to learn the basis function, keep the basis function fixed. When a new function comes in, you learn the coefficients. And how do we go from one function space to another? This is where we have the operator. So where we learn the coefficients in the input space and learn to map one set of coefficients to another set of coefficients in the output space. If you have a completely linear system, it's basically a matrix operation, and it's fully linear. If you have a nonlinear system, you're trying to map a low-dimensional coefficient space to another low-dimensional coefficient space using a nonlinear operator like a neural network. So we also leverage in linear space, you can do singular value decomposition, eigen decomposition to represent what this coefficient mapping is. So we took some PDE problems like elastic plate with a hole, and we represent all the forcing function as input space. And DeepONet is a very popular operator learning approach, which allows you to do something similar. But here we're showing like we can, by separating the input and output space, we are able to do much better representation, and we're no longer limited by fixed sensor locations and so on. Do a more complex Darcy flow, and you can see the blue line, which is ours, able to capture the dynamics really well in flow type problems. But the issue is not just go from input to the output space, we can go backwards, which is your state ID, your system ID. But you have your result and you want to know what is your material ID or forcing function is. And this inverse problem is often ill-posed because you have multiple possible solutions giving you the same final answer. So in this case, rather than trying to do a deterministic mapping, we are trying to learn a distribution over the input space because we know multiple input parameters can give you the same result. So we learn the distribution over that input space. So this could be your invertible neural networks or VAEs, which are conditioned on our coefficients that allow us to do this inverse problem. So the same thing, if you just had a matrix in your linear operator, invert your matrix and you're done, which is a deterministic problem. But if you have a uncertainty or distribution, we can use a conditional VAE techniques to learn the distribution. So for example, if you do a conditional VAE, you can see how we get distributions over the network, which roughly maps out the uncertainty from our ground truth systems. You could do wave scattering type problems, or you could do like more complex like sound wave propagations on complex geometries. In all those cases, we were able to recover back the input functions with like a very low uncertainty bounds. So that's been the dynamics of the system. Now we're going to try to see if we can use it to do control representation. So you do have different types of controls, like model-based predictive controls, PIDs, or you have reinforcement learning. It's just neural network learned controls like PPOs, where you need millions of iterations, each representing your state, action, and reward. Do it a million times to learn a policy. Or what we're developing is called a differentiable predictive control, which is basically take a neural network-based policy, but instead of using a black box simulator which takes a million iteration, we take our differentiable simulator and backpropagate our control policy through the entire simulator. So instead of using a black box simulator, by using a gradient-based simulator, we say is like the gradients give us the extra information we need. So rather than needing a million iterations, we only need 10,000 to 50,000 simulations to be able to do our control policies. So the first step is we are going to represent the simulator as a surrogate model. Rather than using GNS, we are going to use the simple basis-to-basis learning that we've seen before. So our algorithm one is our offline training, where we have different system trajectories. We learn the basis function that represents the dynamics of the system. So same as the B2B approach that we have seen before. And then we're going to keep the basis function fixed and use or learn the differentiable control policy. So the basis function is fixed, but the simulator is fully differentiable. We have a reference and we have a target, see what our function encoder or basis-to-basis simulator predicts. You compute the gradient, backpropagate through your simulator, backpropagate through your neural network policy to be able to condition your differentiable control policy on different input conditions and parameter spaces. So finally, once you've conditioned these input spaces, you now fix your neural network. You get a new set of trajectories. You basically use your function encoder to compute the coefficients. Your control policy is already conditioned on these coefficients, so you now do a zero-shot adaptation to your new problem. So here are some examples. So we have this galactic oscillator. On the left-hand side is your white box Casati type controls. And here we have a saturating control. So that's our upper bound. And this is our learned function encoder DPC type control, where the function encoder represents the dynamics and DPC is our learned differentiable control. You can see we are able to do the control reasonably well until we saturate on the control commands. I think this is the 20 quad rotor control. The first 20 seconds, we initialize the quad rotor in different conditions and different random noise or disturbances created. And we are trying to see how quickly can we stabilize the quadcopter without causing it to fail. And this is the switching region. And you can see most of our cases, we are able to reach a stable state. This is just a van der Pol example where we're showing the zero-shot condition where we are training the state system parameters in a completely new space outside the training range and still be able to achieve a reasonable good control. The goal here is the basis function the function encoder learns is broad enough that it captures the entire sets of dynamics, and you're basically conditioning your control policies on these coefficients. So even if you are seeing a completely new system, it is still represented in the same Hilbert space. So the coefficient does a smaller, lower dimensional manifold where you can do this control operations. So far, we've seen the function encoder applied to the dynamics of the system, which has been representing my area. Now, this is a new area for me is, can we represent the control policy in Hilbert space rather than the dynamics alone? So what we do is do the same thing. Instead of using the dynamics in function encoder, we are trying to learn the control policy and learn an array of control policy that spans a Hilbert space. And we have proved that our control space is broad enough that any approximation that we can do with the function encoder, we could control what the error is, and we get about like 70 times faster than traditional MPC type control. So here's a bicycle model trying to navigate, go around obstacles. These are worst performing cases, and we have a zero-shot transfer of policies as we add multiple obstacles in the system. So you can see from single obstacles to multiple obstacles. We also had quadcopters doing these type of the good thing is it does two things. It does state ID to identify the system, which is compute the coefficients. And then you now have your control policies, which are also in coefficient space. And it is able to get a reasonably good prediction and control costs here. So putting this all together, we want to close the gap. We already showed you how to go from reality or the world model to simulation. So this is our reality. We are trying to do an excavation with a robot, and we record a video, calculate the depth map, and then this is our physical splat. So same as before, where we see that reality. This is our physics-based simulator, which is capturing the same dynamics. And now we can control the splat motion with graphs. So take the robots, describe each of its connections and degrees of freedom as a graph, and be able to simulate it. So on the left, what you see is a simulation and not a real behavior. So we basically take the real-world video of our excavator and then be able to figure out where the joints are and how to manipulate it. And then once you're manipulating it, now we can put it all together is like do a virtual experiment and do a physical experiment, differentiate it until we identify what is the state ID. In this case, what is the material ID, identify what is the friction angle, and be able to now use that differentiable GNS. In this case, we haven't done DPC yet in these problems, but so far we're the amount of state that we need to describe during an excavation type simulation is large because of each sand particle has its own state, 6 degrees of freedom. So right now we're just doing an MPPI type rollout. So do thousands of trajectory rollouts to see what's possible, and do that excavation here where it is trained, identify the system base. So the first part, it is going to do the system ID where it scoops up a little bit of soil, cores it out, and then that allows it to learn what this system is. So once it learns the system, what I don't show you is all the time it pauses and starts to do an MPPI rollup. It takes about 2 minutes to do the whole thing. You're seeing a 30-second video. So 2 minutes is the amount of thinking. So 5 times slower than what it is doing. But once it learns it, this is the MPPI's rollout policy where it's able to create that little trench that we asked for. It's still not perfect, but it's our first iteration of control in a very high dimensional state system. So where are we going with all this? Is these that's the RC car which we have. It doesn't. Sorry. The RC car over here on the left, it drives at 50 miles an hour. It doesn't show you the scale. It's about a meter long. And we've been using function encoders to represent both the system dynamics as well as our control policy. We have been testing it on ice rinks. So our goal is to drift at 50 miles an hour on ice, and also drive around sand materials. Eventually go to this where we have multiple robots actively trying to change our environment. In these cases, you run into issues where the dynamics changes so much that you don't want the rover underneath actively sabotaging the one at the top. So how do you share the state space which they are in? How do you manage your control policy and potentially provide guarantees or uncertainty bounds to our policy? On the right-hand side, we splatted and made physics for this course. Like this is our assault course where defense trains. It's part of ET, and we have these rovers and leg robots. Rover has autonomy. The leg robot doesn't, but we are still in early stages of autonomy for that, so it's stuck here. So we want to be able to get out of these situations and be able to offer optimal control policies. So that's the pipeline which we've been building, which is see, sense, and splat, get the predictions, be able to control it, and we're entering the policies where we can give guaranteed bounds of what our control would look like, what the dynamics would look like when I do certain types of control. And I feel like the differentiable aspect of this entire pipeline from seeing prediction to control gives us a new way of doing world models without where people typically forget physics, and we want to entertain physics and numerical methods and be able to guarantee this control. So some of the projects we are currently working on is building on the moon. So be able to manipulate materials on the lunar surface purely through perception, and we want to be able to build like landing sites for next rockets, like clear out all these rocks, be able to navigate over them. I showed you some applications of air-ground teaming where we want to be able to figure out where to navigate, especially in like hostile regions. This is another interesting area when shown much, is so far the environment has been changing. It's been soil mainly, but now we thought deformable material is the same. So instead of the environment changing, here the robot is actually changing. So we have a rover, just about $1,000. It's a cheaper size one. But our goal is, rather than build quadcopters, which can't carry heavy loads, we are trying to use parafoil drones. So this shows you the scale. That's a undergrad student for scale. And we want to be able to control these. We're going to control these cables, and we are going to control it based on the images that we capture from the parachutes. There are two things. We need to go from vision to dynamics, but also do control in terms of predict ahead or look ahead cases. So this is our GNS application. So rather than GNS on particulate material, we are doing it on mesh-based systems, so where we can model the cloth and look ahead what the wind could potentially lead up, and then predict what our response would look like. So we have built this rover. It's on currently testing. We can't fly it because we are on the heavier side, which we need license for. But we can do all of these active controls on the ground with the rover driving on grass, and be able to control with like 6 linear actuators. This is our Center for AI in Engineering. We have some online courses on scientific machine learning. Also have PhDs or postdoc positions if someone's interested in. Thank you so much for having me.